Hey kids, it's another lesson. You'll notice today I've got a beautiful light because it's the sunset. So, an evening edition of Parabolas. Let's go. So, believe it or not, we're actually continuing along with parabolas here. We have done a bunch of stuff. We have looked at vertex form, general form, and factored form. The last thing we're going to do is we're going to look at the concept of whether parabolas are positive or negative. That's basically what the next two lessons are going to be about. So what we've done so far is we've had a graph like this, y equals x squared plus 3x minus 4, and we've figured out where is it equal to 0. So we've learned how to solve that, we've learned how to graph it, and all this good stuff. Today we're going to ask just a very simple question. Not when would x squared plus 3x minus 4 be equal to 0, but I could ask you something like when is it greater than 0, or when is it less than 0. And when you have a graph right in front of you, it's actually pretty simple. You can see very clearly that when x is negative 4, or anything less than that, the graph is above the y-axis. So we can say that if we're looking for the values of x for which y is greater than 0, we could say x is less than negative 4. And we could also say x is greater than 1. Where we're going to end up is when we have an equation like this one here, and I haven't shown this, but this one right here, so I'm going to hide this one, negative 2x squared plus 3x plus 5. When is that greater than 0, for example? This is a whole different ballgame, because when you don't have the graph in front of you, you actually have to do a little bit of thought. And you could sit there and you could figure out when it's equal to 0 using all the stuff we've learned in chapter 3, but that doesn't really answer the question of when it's greater than 0 or when it's less than 0. So we're actually going to have to use those techniques plus a little bit more thought to answer this question. If you're a curious person, you could think about this, pause the video, I'm just going to show you in just a sec, but can you look at this equation and get a sense of when this graph would be greater than 0? I'm just going to show it here so you can see. Boom, there it is. Okay, so you'll notice if you actually solve this by factoring, you would have found the two x-intercepts to be negative 1 and 2.5. How did you know that the parabola was greater than 0 between the two intercepts and not like some other situations where perhaps it was flipped the other way around? So what you can do is you can use some logic here. You can say there's a negative sign out front, so therefore it's pointing down. And you could say, well, if I know it's crossing the x-axis here and here, it's pointing down, it must be shaped something like this, and it must be greater than 0 between those 2 points, and you could write that accordingly. If we switch this to a positive, and maybe I switch this to a negative, like maybe I switch the sign of everything, I guess I'd have to even switch the sign of this middle one, then we would have the reflection of that, and everything between those 2 points would be negative. Anyway, we're going to look at that and a whole bunch more stuff and get a little bit of sense of why this is useful in the next 2 lessons. All right, so let's have a look here. So starting from the beginning, this is section 4.8. We are solving inequalities graphically. Okay, so the first thing I'm going to show you is a linear inequality. So if I ask you to solve 5 minus 2x is less than 3. So this is like saying, well, here we go. This is like saying for what values of x does the line y equals 5 minus 2x drop below the line y equals 3. So one big important thing is we have to understand that this half is its own line. Y equals 5 minus 2x. And this half is its own line, y is equal to 3. And when you put these together on a graph, you get this line going down. So it's got a y-intercept of 5 right here, and it's got a slope of negative 2x. Or sorry, just negative 2, not negative 2x. And of course, when is it actually crossing over this line of y is equal to 3? And if we're asking when is 5 minus 2x less than that, we're kind of asking for what values of x is the line less than. So we can see all of this here is less than the line y is equal to 3. So those corresponding x values is right here, and everything to the right. So what we can do is we can look at this graph and we can say x would be everything bigger than 1. So when we look at the graph, of course, that's what we can see. We can see x is everything bigger than 1. If you want to show the solution on a number line, there's just a couple little technicalities here. We can draw a number line like this, and we can say here's 0, here's 1, here's 1, and here's 2, and 3, and so on. how do we show it on a number line? We want to say when is the line strictly less than. That's what this sign up here means. So we would say it cannot equal 1, but it's everything bigger than 1. So what we do is we put an open circle there, and we put a solid line going to the right. And just a little reminder, an open circle means this or this. It does not include the point. Should have put a period there. Okay, so that's the idea. Now, if you want to do this without necessarily looking at a graph, is we can move all terms on one side and make the other side equal to 0. So one way we could do this is by saying this business here, we'll take 3, we'll move to the other side, we'll subtract from both sides, and we could say 2 minus 2x is less than 0. So this could still be done graphically, but you could also even do this algebraically. We're not going to focus on the algebra time too much here, but we're going to just think about this. So another approach would be to do it this way. Okay, so in this case, I'm going to erase that so it's not like. Now you must determine when the line y equals 2 minus 2x is below the x-axis, because remember, this is kind of like the line y is equal to 0. So one thing is, this is a little complicated. Making one side equal to 0 can sometimes make your life a little easier. So instead of this picture, this isn't really what's going to go on. In fact, what we're going to do is we're going to wind up having 2 minus 2x is actually more like this line here. And again, we can see that when x is anything bigger than 1, we're going to have a solution. Now, the reason why I'm mentioning all this is because when you're solving inequalities, x-intercepts get to be called critical points. The reason why they're called critical points is because they're very important. In this case, this point right here is critical to know, because if we're asking when is it less than 0 or when is it greater than 0, this is going to be very important. Critical points, very simply, represent the end points of an interval of solutions. Okay, that sounds like a mouthful, but basically what an interval of solutions is this. Okay, we're not saying x is equal to 1 anymore, we're saying x is greater than 1. So an interval would be all the values that satisfy it. So when we say something like x is greater than 1, this is what we would call an interval of solutions. And again, on a number line, it would look like this. Here's 0, here's 1, and it would go like this. Okay, so that is the interval of solutions. It's not just a single point, it's a whole bunch of points. Okay, so here's the thing. Now, when you solve an equation, what you can do is you can substitute your equation back to see if the equality is satisfied. So what's going to happen here is we're going to pick some value. So when you solve that inequality, we're going to pick any value, and this is key, any chosen value from the interval better satisfied. And any chosen value from that interval gets to be called a test point. So while we can solve totally graphically, we can also do a little bit of algebraic stuff. So for example, let's just get to this point here. Any test point on the correct side should satisfy the equality. So total, for example, let's see if I'm going to move forward. No, okay, we're good. So the solution of 5 minus 2x is less than 3, is x is greater than 1. Okay, we solved that on the last slide. If we want to check the solution using a couple of test points, what all this is saying, this kind of can sound a little complicated, but it's actually really simple. What are the possible values of x that should satisfy this? Well, according to our answer, x is anything bigger than 1. So pick a number bigger than 1, and if I put it back in here, it should work. That's what we mean by a test point. So what are some test points? Possible test points could be x is equal to 2, or 3, or 10, or honestly anything bigger than 1. So if we actually check this, we can say 5 minus 2 times, let's pick the first one, 2. Is that less than 3? So that's 5 minus 4 is less than 3. Yeah, that checks out. Let's pick the next one. 5 minus 2 times 3. Is that less than 3? Well, that's like 5 minus 6, which is negative 1. Absolutely. Same with 5 minus 2 times 10. Well, that's 5 minus 20. Yeah, you bet. Okay, so as long as x is bigger than 1, we're going to have some some expression here, 5 minus 2x is going to be less than 3. And this should sort of make sense because you're going 5 minus a number. The bigger x gets, the bigger the subtraction number gets, and the smaller the left side will be. So that's what a test point is. More on this later. Okay, so if you want to solve this bad boy here, solve 2x plus 3 is greater than or equal to 1 minus x by graphing. And then we're going to show it on a number line. All right, so let's have a look here. So we've got 2x plus 3. So one of the reasons why we're doing this is just a little refresher. We have to graph y equals 2x plus 3. So we're going to remember from grade 10 the y equals mx plus b idea. So we're going to start at 3 and we're going to have a slope of 2. So we're going to start at 3 and we can go over 1 up 2. Then we go 1 to the left and down 2. 1 to the left and down 2. 1 to the left and down 2. Okay, so that is my line. Y is equal to 2x plus 3. The other side would be y is equal to 1 minus x. So we're going to start here, and we're going to have a slope of negative 1 because that's a minus x. Go over 1, down 1, over 1, down 1, down 1, over 1, down 1. And then we're going to go here, here, here. Okay, so 1 minus x is going to look something like this. All right. Okay, so what I can see is they're crossing over here. Now, normally, well, not necessarily normally, but a lot of time you're going to find your solution is something nice and easy to get. Now, in this case, I can actually see that my solution is right there. So when I want to solve this, when is 2x plus 3 greater than 1 minus x? I can see what's happening here is if we go down, 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 down to about here, I'm going to say this is probably x equals, I'm going to take a big fat guess. I'm going to say it's probably about negative 2/3. I actually don't know that for a fact, but we can figure that out later if we really want. I can see for all the values of x there, this section here, which is y is equal to 2x plus 3, I can see that it's higher up. It's physically above or equal to 1 minus x. So as long as this section of the line is above this section, it's a true statement. So for all the values of x corresponding here, it's all of those. Now I would like to know exactly where they cross over. So if I want to know this exactly, we can find the intersection point. We can say 2x plus 3 is equal to 1 minus x, and this is not really a hard thing to do. We'll move that to the other side to get 3x, and we'll subtract that over there. And lo and behold, hey, my guess was absolutely correct. X is equal to negative 2 over 3. So what we can therefore conclude, therefore, x would be everything bigger than or equal to negative 2 over 3. So one thing that really gets people in this unit is you're sometimes solving using an equal sign and sometimes writing a greater than or equal sign. So what I just did is I solved when the two lines crossed over. That's why I used an equal sign here. But then I want to say, okay, well, at that intersection point, that's a true statement that 2x plus 3 is greater than or equal to 1 minus x. And then I can see it's greater than everywhere else when x is everything bigger than that. Okay, so that's showing our solution. We'll show it on a number line. If our number line looks like this, here's 0, here's negative 1, here's 1 and 2, and so on. It doesn't really matter. And we'll write negative 2 over 3. So we're going to put a solid dot there because it's greater than or equal to negative 2 over 3. We're going to say it's everything bigger than that. So we're going to put the arrow going off to the right. Okay, now we want to check your solution using 2 test points. So let's pick a couple test points. So if we want to test this, we should say x is equal to 0. That's a fine solution. It's bigger than negative 2 over 3. And I'm going to use x is equal to negative 1. Or sorry, just pause it like that, right? Okay, so x is equal to 0. So is it true that 2 times x plus 3 is greater than or equal to 1 minus x? Well, what's this? That's gone. That's gone. Is it true that 3 is greater than or equal to 1? You bet. Same thing. When x is 1, is this still a true statement? That's 2 plus 3. Is that greater than or equal to 0? Yeah, that's true as well. Okay, so it does check out. So we used a couple test points and checked it. Okay, so now we're going to take this idea and we're going to go to inequality. So if I ask you something like solve x squared minus 2x minus 4, when is that greater than 0? This is the same thing, except now we're talking about when is this parabola here greater than 0? Or when is this parabola above the x-axis? So if I want to answer this question, I can see on this graph here, we've got a couple critical, okay, let's not jump ahead too far. We've got a couple critical points. Right here, x is equal to -1, and right here, x is equal to 4. Those are the critical points because those are the x-intercepts, and that's when the parabola switches from being above the x-axis to below the x-axis. I don't know why I'm having such a hard time saying that right now. So the critical points are x equal to -1 and 4. The solutions are, now we can see if we have an actual graph here, the solutions are, when is it above the x-axis? Well, this section here is above, and this section here is above. So the corresponding x values would be any value of x that's bigger than 4, so that's all of these, and any value of x that's less than -1, so that's all of these. So the solutions would be x is greater than 4, or x is less than -1. On the number line, we would write this like, so we'd have our number line, and it would go something like this. Here's 0, here's -1, and then we have 1, 2, 3, 4. I know this is not to scale, but it doesn't really matter. We just sketch an idea here. What we would do is we'd say, because these are not equal signs, we're going to put open circles. So an open circle is going to go there, and it would be x is greater than 4, and it would be x is less than -1. Okay, now we've got one more problem here. The Awesome T-Shirt Company makes custom T-shirts for $12 each, plus a $50 processing fee, and the best does $75 and $10 per shirt. How many shirts would you have to order to make the best company the better option? Solve using graphing technology. Okay, so what we're going to do is we're going to take a sec here. If you haven't done any thinking, pause the video and think about what the equation is going to look like. Okay, so the Awesome Shirt Company is going to be $12 per shirt plus a $50 processing fee. So first of all, I want to define something. I want to say let x equal the number of shirts. So awesome is going to be 12 times the number of shirts plus $50 just to do the job. And best is going to be $10 per shirt, but $75 to do the job. So we want to make best the better option. Now, if you want to be the better option, you're going to cost less money. So what we want is we want the cost of A to be greater than the cost of B. That's how we're going to make best the better option, by having it cost less. So this is going to wind up being 12x plus 50 is greater than 10x plus 75. So if we want to actually answer this question, then we're going to say, all right, so we can either draw it by hand or we can use graphing technology. So I'm going to use graphing technology because that's what I'm saying to do. I'm going to jump over here to Desmos, and I'm going to do a little bit here. I'm going to say, let's get rid of that. I'm going to write, let's make sure I have this correct. So 12x plus 50, I'm going to show it, and I'm going to say the other one is 10x plus 75. Now, I could have solved this mathematically, but I can also use a graph here. So if I use the graph, I have to go all the way up, all the way up, all the way up. I want to see where they actually cross. Okay, let's go way, 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 way up. Okay, I'm going to zoom out here. Let's go way, way, way up. So Desmos is nice because if you kind of find roughly the spot and you click on it, it'll usually find it for you. There we go. So we can see they cross over each other at x is equal to 12.5. So the best company is the red line, and the red line is below the purple line. So the red line costs less. Keep in mind, this is a graph of cost. So when we sell 12.5 shirts, so what we can see is when x is greater than 12.5, best costs less than awesome. Okay, now you can't really sell 12.5 shirts, so what you would logically conclude is you would say, therefore, x would have to be greater than 13. Now you might even say greater than or equal to, because 13 would actually count, so I think we would include that there. strictly 12 and a half, but x is greater than or equal to 13 would be the most sensible answer. Okay, one last question. So here's a fun one. If anyone ever wants to make a math problem with a parabola, all you have to do is throw something up in the air, because all things thrown in the air make parabolas. So ball's thrown up in the air, its height is described by blah, blah, blah. At what time does the ball no higher than 3 meters? Use graphic technology. So I'm just going to actually take a second to roughly sketch a graph here, because this is the idea. The height is a function of time, meters time. And this is my parabola, okay? So we recognize it's a parabola because it's got something squared. Now I know it's got a negative sign in front of the t squared, so it's going to be downward facing. So maybe it looks something like this. And we want to say, at what time is the ball no higher than 3 meters? So if you're looking here, this is 3 meters high. And again, this is just a sketch, but we want to figure out how we can answer this by using graphing technology. So if you use graphing technology, it's pretty easy. If you do it with algebra, it's quite a bit harder. That's actually the next lesson, but I just want people to get used to the idea here. So what we would do is we would say, when is 16t minus 4.9t squared, when is that less than 3 meters high? Now it also says, when is the ball no higher than? So it has to be less than 3, and it could actually be equal to 3. One of the biggest things is just interpreting this statement as greater than, less than, or less than equal to, that kind of thing. All right, so now for doing this with graphing technology, you can do it this way, or you could even move everything over to the same side. It doesn't actually really matter. I'm going to leave it like this. So what I'm going to do it with graphing technology, on one side I'm going to write y is equal to 16t minus 4.9t squared. You know what, I'm using Desmos, so I'm not going to use t. I'm going to use x because Desmos likes x. It's programmed to understand x. So I'm going to actually type into Desmos 16x minus 4.9x squared. This I'm going to type in y is equal to 3. That's pretty simple. So we're going to go over to Desmos. We're going to have a little look here. And we would say 16x minus 4.9x squared. There's my parabola. I'm going to just zoom my screen in normally, and here's y. Let's go y is equal to 3. One small thing, I don't have to type in y is equal to when I'm doing something in terms of x, but if I'm just doing a number, I gotta make it clear. Okay, so on the graph here, I can see I've got 2 points here, here and here, and the question is, when is it no higher than 3? So what I can see is this section right here, it's less than 3 meters high, and same with this section over here. So my two values are 0.2 and 3.066. So on my graph, this corresponds with x equals 0.2, and this corresponds with x equals 3.066. I got that number right? Yes, I did. So what I can say is this portion here and this portion here is less than 3 meters. So what I can therefore conclude is I can say x is less than or equal to, because it's allowed to equal 3 meters high, 0.2, or x is greater than or equal to 3.066. I guess I can therefore conclude that the time, because remember, we're talking about x, we got to talk about time because it's a word problem. Time is less than 0.2 seconds or more than 3.066. And again, I just realized I made a tiny little mistake. It's not less than, it's less than or equal to. Same thing here, more than or equal to. And of course, take a second to think about this. We just did a bunch of math, but does this make sense? At what time is the ball no higher than 3? So when you answer this, you say the time is less than 0.2 seconds or it's more than 3.066. So if you threw a ball in the air, when the time starts ticking, the second leaves your hand, it's going to take a little bit to get to a certain height. Now, it's going to be less than some sort of time, right? 0.2 seconds, so 0 to 0.2 seconds. But it's also going to be more than 3.066, because if you throw something up and you wait 3 seconds, chances are it's going to come back down already. And any time greater than that, it's going to be down low. In fact, it's going to hit the ground. So this should make some sense, I believe. Okay, so as far as I know, there we go. That's it. That's the lesson, and we will see you later.